So my name is Peter Richo. I'm the CEO of MEMS Imaging. We are an independent service organization that focuses primarily on imaging equipment. And for that, we're talking about X-ray machines, ultrasound systems, CT scans, OPG, mammography, IOPA dental systems, MRI systems, and basically everything around the imaging arena, where we work with installations, repair and maintenance, sourcing of spare parts for these particular systems. I'm very honored to be here, and I hope that our discussion is going to be very fruitful and very helpful for everybody who is here. I am aware that some of the people who are in this particular session are also Kenyans. So, for the Kenyans around, welcome very much to this. And for my friends from India who have actually organized this for us, we also like to welcome you to this. So, we are going to focus on three different modalities. In actual application, when we talk about what is called a modality, it's actually the kind of the kind of hardware that is actually used, or rather the kind of application that we are using this imaging equipment for. Because of that, then we are having something like X-ray. So we have different kind of management. So we have in X-ray, we are having something different from whatever is in ultrasound, something different from whatever is in CT scan, from mammography. All these different applications of imaging systems are what we normally call modalities. Yeah. So the modalities that we're going to be looking at today are X-ray, CT, and ultrasound. So so and for these particular systems, we are going to be looking at what are the major manufacturers for these particular systems on a real world environment, not really about theory, but on a real world environment. Who are the major manufacturers of these particular systems, and how do they work? So, in the world, we have, I would say, five major manufacturers of all imaging equipment. We have GE, we have Philips, we have Siemens, we have Toshiba, which was now acquired by Canon, so it's now called Canon Medical Systems, and we have Hitachi, that was acquired by Fuji, so Fujifilm, which actually is one of the other major ones, and then also somebody like Agfa or somebody of sort, right? In addition to that, we have companies that specialize only in the manufacture of X-ray generators, and they sell the generator plus the console plus the tube. So we have companies such as one company actually from India, it's called Ionics. That is their job. So they sell just generators, and then manufacturers basically assemble them into their own table or something of the sort, and then they are able to sell those particular systems. So for such manufacturers, I think the major ones are one company called IMD. We have Ionics from India, and another major company from Italy. It's called Sedecal. Majority of these companies actually come from Italy, that are manufacturing just generators and then selling them for somebody to assemble them in their own way. Yeah. Uh, of course, also there is a huge part of one modality that is often overlooked in radiology is what we call HCIT, so healthcare IT. In healthcare IT, we have Such systems such as pack systems, which are um, storage systems for radiology images. Um, we have hospital information systems. We have what they call from hospital information systems basically is something to manage the full hospital. So it might have extra sections that deal with the radiology part, some of them that deal with the laboratory part, some of them deal with actually booking of the patients and everything else. So all of that is all of these are modalities. Even HCIT is a modality. Everything that is used in a particular way is a modality when it comes to imaging systems. So I will dive into the X-ray systems and what I hope to be able to do actually across all the modalities that we're going to be speaking for is give an idea of um, how this particular system is structured and what are the commonalities that are shared across these particular systems, and give some idea about generally as engineers what to look out for in these particular systems. So for X-ray systems, um, generally all X-ray systems will have around 5 different units. So we have our generator. The generator's job is basically to create high value power that then is transferred into the tube, and, and which actually takes us to the next major important part is the tube. And then you have the detector, we have the console, and we have basically what we call the gantry. So you can call it the table plus the chest stand, but generally in imaging terms we call all of that unit the gantry. Yeah. So when you go into something like the generator, we have two different major types. So we have what we call the line frequency generators, and we have what is called the high frequency generators. So the line frequency generators, generally what it means when you're talking about the frequency of the generator is how do we create high power. The job of the X-ray in a nutshell is that you have this particular unit, this particular power supply, whose job is to create very high voltage. And by high voltage you're talking about 80,000 volts. Whenever you talk about maybe something like in terms of uh, specifications for an X-ray, um, these we have what is called like the kV, we have the MA, and the time. These three things, they are called the techniques of the generator. So kV basically is kilovolts, which is actually the amount of voltage that is between the anode and the cathode sides of the tube. Because we are all engineers here, I think everybody here has had some experience about an X-ray system. So I'll just put it at that. So we have kV is the actual high voltage between the anode side and the cathode side. MA is the actual amount of current that flows between the cathode side and the anode side while you're doing an X-ray, and time in terms of S is how long that you're trying to radiate a particular place. Okay, so in terms of what I was talking about, high frequency and low frequency, high frequency and line frequency of the generator is generally you need to provide this high voltage. So when you talk about for X-ray systems, it ranges from 40 kilovolts all the way to 150 kilovolts. So you're talking about 40,000 volts. How do you create 40,000 volts in a small environment that is then able to be used by the tube? You must have a transformer. Okay. So the older systems used to use the line frequency. For us, for our case in Kenya, we are using a line frequency of 50 hertz. In America, I think it's 60 hertz. It's generally around 50 and 60 hertz. I'm not very sure what is actually used in India, but that's generally how it's done. So uh, you need a generator. Now, the older systems were using the same 50 hertz that's coming from the power. You have a generator and you have a transformer inside the generator, and the transformer's job is to basically step up this particular voltage. But there was some inefficiency to it, and that's why I think if you look at some of the much older X-ray systems, they had a very big transformer that was always put towards the side of the room. Nowadays, that is not so common because we have migrated from line frequency to high frequency. There is a lot of losses from a line frequency system. They are called eddy current losses, and they generally lead to a lot of heat being generated in the transformer. So the transformer has to be big to allow for the heat dissipation from the coils of the transformer. And this problem actually has gotten solved um, by use of high frequency systems, where majority of generators that come today, that are actually coming from the manufacturers today, will have three major components. So we'll have a rectifier. We have the power that is coming into the generator. We would have a rectifier there, and then we would have what we call a chopper circuit. So it's an inverter. I like to call it a chopper circuit because that's actually what it is, but generally it's an inverter. So the job of the inverter, you have a rectifier that transforms the power that is coming in as from AC power from the sockets or from the electrical distributor. That one is rectified into a base DC voltage, and then the DC voltage, and then you get an inverter for it that then chops at that particular power at a very high frequency in the range of kilovolts, no kilohertz, and then this power then is sent to the transformer. From physics, if you increase the frequency of a sinusoidal wave, or rather of an electrical wave, if you increase the frequency for it, then um, during conversion, when you're stepping up the voltage, you are able to minimize the eddy currents. Yeah, eddy currents is basically whenever you are having a coil for a transformer or for an inductor or something of the sort, if at all this current flowing through it, it induces a current that is opposite to what it is. So generally, there's a creation of a resistance across that particular coil that then prevents you from running a lot of current through it. Okay, of course, we know that if you run current through a high resistance, you have a very high voltage difference between the beginning and the end. So by using high frequency, they're able to reduce that eddy current. Able to reduce eddy currents, then they can use much smaller coils and a much smaller high voltage transformer. This is common in almost all of the X-rays that are coming right now. It's very rare to find an X-ray that is coming right now with a low frequency, but it's important to understand how that generally works. A key differentiator for the generator is the power rating for the generator. So all generators, you will see there is a sticker that will show you how many kilowatts the generator is for. So you have 10 kilowatt systems, 20, 30, 40, 50. I think right now majority of them for high functionality generators, we have around 50 kilowatts. The other thing that is a key differentiator for generators is the amount of power that is supplied to the generator. So generator is basically the heart of the X-ray machine, and we have either systems that are using three-phase power to supply the generator, or single-phase power, basically a line and a neutral to supply the generator. So those are key differentiators. When it comes to the tube, all tubes have particular specifications that are then used. We have what is called the anode heat capacity. So think about it like this. So you have a particular tube. In the anode side, you're hitting this anode with high-speed electrons, and almost 99% of all of the X-ray energy is transformed into heat. So you need the anode that is actually that's where the heat is being concentrated, to be able to absorb this heat and to release this heat to the environment. So the capacity from the design of the particular anode is what is called the anode heat capacity. So that will always be written in terms of mega heat, mega heat units, MHU. It's always going to be written on the tube. The other thing that is different about particular tubes is the maximum power rating for it in terms of the kV. So all tubes will have particular rating. Maybe it's maximum for it is 125 kV, 150 kV, different depending on what kind of a tube it is. That's one other thing to check on. And the other major thing about tubes is that we have what is called the focus. So um, in in X-ray systems, you have what we call like the small focus and the large focus. The focus generally means is that for the tube, we have a filament that is heated, basically like an incandescent bulb. It is heated, it releases electrons. The electrons are accelerated towards the anode by applying a high voltage difference between the cathode and the anode. Okay, so um, many X-ray tubes will come with two filaments. We have a small filament, which is a thin, it's a shorter filament in terms of length, and a large filament. And these are used for different applications and for imaging of. If you want to image something that is very, very fine, like a blood vessel, you generally use the small filament. If you need to image something that is much larger, you'd use the large filament. But majority of tubes come with this. Um, and therein comes a way to actually test a tube for a diagnosis, for a diagnostic person. If you need to confirm that X-ray tube is not defective, all you need to do is just take your multimeter, put it into resistance mode, and then you're able to measure from the tube. There it's gonna be marked like one is a C and an L and an S. So C is for common, L for large, S is for small. If you're able to measure resistance, and the resistance is very, very small, maybe around 1.2 ohms, uh, 2 ohms, 3 ohms, something of the sort, very, very small voltage. If you're able to measure continuity, or rather that resistance, then you're actually pretty sure that the tube should be okay. Um, but of course, there are other different failure methods for the particular tube. And that's all about the tube. So the next thing is the detector, of which this time now in this recent future for us, we are moving into digital radiography. So from there, you'll actually hear terms such as DR and CR. CR basically stands for computed radiography, DR for digital radiography. So this is how the system, the X-ray machine, is able to convert the X-rays that pass through the particular person's body into an image. So in the physics of detectors, you have basically something that filters the amount of X-rays that are going to the detector, and then you have something that glows once it's heated. It's hit by X-rays. Once it glows, then you have some photoreceptors on the other side, uh, whose job is basically to take the amount of light that is actually irradiated by the glowing mechanism, and convert that into electrical signals that are then uh, read by the computer, and it's regenerated into an image. So CR is the older types, old from long ago. What you used to have was a dark room where you develop the images, like a photo studio, and then you moved into CR systems. So you have a cassette, and inside the cassette you have what you call an imaging plate, and the imaging plate is the one that holds the actual data from the examination, and then the imaging plate is one that is actually read by what is called the CR machine to create an image now on the actual X-ray system. Uh, Now, the current trend right now is to have what we call DRs, stands for digital radiography, and whose job is basically just to do the same thing as a CR, but now you don't have to remove the imaging plate. the imaging plate stays constant there, and then everything is read via Ethernet cable or via wireless by the PC, and all that generally works in that particular way. The other thing is of course, the table, which I call the gantry also. One important consideration about the gantry, we have generally two types. So you can call the floating gantry, no, rather the floating table, and a fixed table of sorts, right? Floating table basically means that when you release the brakes, you have the table. You can move the table on the longitudinal direction and the lateral direction, and maybe even for some other systems, you can move it up or down. Generally, all these tables will work in one particular way, where you have some electromagnet whose job is to um, contact with the rails for the table. So if you release the electromagnet, it's on by default. You need to release it. You release it, then you have some guide rails where the table can move. Um, you know, you stop releasing the brake, and then the electromagnets contact and hold it. Majority of them will work with either 24 volts or 12 volts, and it's almost always it's a DC voltage. So that's one thing to actually check for if you're having a problem with the table or something of the sort. There'll always be a power supply, either supplies 24 volts or 12 volts. Mainly I've seen them with 24 volts. Always there will be a power supply. That power supply for DC volts supplies the table and supplies also the chest stand to move it up and down, the tube stand to move the tube up and down. Almost always it's going to be a DC voltage around 24 volts. And yeah, the one other important thing is the what we call a collimator. So the collimator exists in front of the tube. The job of the collimator generally is to is to um, is to create a good signal. Um, Basically, it cuts out all the scatter radiation, rather radiation that is not strong enough to actually go into a body and just be harmful for the particular person. It cuts all of that through a filter, and then shapes the X-ray, so that whatever is actually going to the patient, it's only very very much focused to the area that they're actually trying to image. So that's the job of the collimator. Its job is collimation. Okay. Yeah, so I think that's it about X-ray systems. So let's go into ultrasound systems. So ultrasound systems are generally divided into what we can call the two major parts. So we have what we call the back-end processors and the front-end processors. Back-end processors basically is a PC system whose job is it's a commercial PC system. Okay, so in the older system, you'd get some HPs inside there, some Dell systems inside there, whatever. And its job is basically to hold the software and to interact with the user. So you need to put in the patient details, you need to save the images. All these are done by the backend because it's a general PC. And majority of the times, for almost all the ultrasound systems that are seen that are modern systems, you have a commercial operating system. So some of them are using Linux, some of them are going to be using Windows, and then you have an application software that is built on top of the operating system. And the application software is where all the difference comes, and so they put in the drivers for the different cards in the PC. That's actually the part that dictates the kind of a communication that's going to be happening uh, with the user. The other part is the front end. So the front end, the way to think about the front end is the actual electronics that are used for translating the ultrasound signals to, creating the ultrasound signals and translating them back, and then sends it to the backend for the backend to actually display it to the monitor or to the screen or whatever. Yeah. So the front end, majority of times, you will have three major components. You'll have a power supply, which needs to provide sometimes up to around 110 volts DC to the transducers, to the probes. Um, you will have basically what they call a relay board. It's called different things in different companies, but I like to call it a relay board, which is where you actually connect the ultrasound probes, and then you'll have, some different companies call them different things, but you'll generally have an analog receive board and then a digital. Analog receive board is basically, so how does ultrasound work? You create sound waves, push them into the body, look back for the reflections. Okay, so you need to be able to receive that reflection, comes as an analog wave, as a sound wave, uh, translate that into a digital signal, um, format that into something, and then send that into the backend processor for viewing of the thing at the screen. So these parts will almost always be there in the front end: a power supply, a relay board, and the electronics to actually um, create the sound waves and to read the sound waves. Uh, because of that, uh, ultrasounds then have different particular uses. From what I've seen, the majority of the uses are either, um, just 1 second, please. Hello, my apologies. Um, okay, so from my experience, we have two major uses of ultrasound systems. So you have uh, systems that are used generally for cardiac care and obstetrics and gynecology. Almost across all the major manufacturers, um, you will have particular systems that are geared toward cardiac examinations, like for GE Systems, which is one of the major manufacturers. These will be under the what we call the Vivid line. So they are geared towards cardiac examinations and continuous wave examinations, and basically everything to do with the heart and the venous systems of the body. Other one that you will have is for obstetrics and gynecology. So basically for maternal health and yeah, for basically for women, right? And then you have generally what we call like for maternal health for GE systems, they are under the Voluson line. So GE Voluson something, okay. And then you have general imaging ultrasounds that can be added some things. Um, in that particular case, what ideally helps the system to be able to do these different things is what we call the probes, or you can call them transducers. And so these probes are common across majority of all the manufacturers. They will have them. They are gonna look differently, but they have similar job. Okay, so the major probes that we have in systems, ultrasound systems, are gonna be linear probes. Basically, look like a rectangle, You have convex probes. You have transvaginal probes, which are called TVS, and you have sector array probes, or rather the cardiac probes, and you have TEE probes. Uh, Stands for transesophageal echocardiogram. Generally a probe that you can insert into the mouth of somebody and push it all the way into maybe like like towards the stomach or something of the sort, and you're able to actually make some examinations for the heart. Mainly they're used for the heart. So you push them in into the mouth all the way up to the chest, and then you're able to image the heart from a different direction. Yeah, so that's kind of the probes that exist for that. Uh, One other major consideration for ultrasound systems, and creates a difference between ultrasound systems, is what we call um, um, the matter of portability. So we have some ultrasound systems that have to be placed in a particular facility. They are operating from line power from the socket, and generally you have to use them in that particular way. And then the other kind of ultrasound systems that you have are the ones that you can basically carry. They look like a laptop, okay? You're able to carry them everywhere and actually do different examinations, and they're mainly used for point of care, which means that the physician is the one that actually goes to the client to do an examination for them. Sorry for that. To make an examination for them. Um, uh, Now we are getting new trends for ultrasound systems. Remember when I told you that they have different ultrasound transducers for different applications? So now in the newer systems that are coming out into the market now, you are having systems that one probe contains everything, you know. So in the transducer, you have all the front end electronics of the system are there. Um, you have um, um, and then only one transducer is used to do all the different examinations. So it's used for cardiac. You can change, because really what is different between these different transducers is the frequency range they play in. So you have very high frequency systems and you have very, very low frequency systems. I'm not 100% sure about this, but I think low frequency systems are used for deeper imaging. High frequency systems are used for more surface imaging. Okay. So now you have probes, the newer trends that are coming into the market. You have probes that are able to make all these different. They are able to play in all these different frequency ranges, and this probe, just one unit, you connect it to your phone or to your laptop via Wi-Fi. You are able to image and do all these different examinations. So it means now in the newer trends is that you don't need to actually have an ultrasound system. You just have a phone, an application, and a transducer. So that's the new thing. I haven't seen many of them yet, but I'm pretty sure that in the more advanced economies, that is something common to find. Um, one one important consideration for ultrasound system are what we call the options. So an option is a software license to activate a particular application. Okay, so ultrasound systems, the way major manufacturers do them is that are created all it's capable of doing many different things, but depending on the package that you purchase, uh, only some things are enabled. So an option is something that either maybe some kind of a key, of a license key that is input in the system to enable the system to do a particular thing. Okay, so maybe you have a system that doesn't is not um, by default does not do cardiac examinations, but all the hardware exists in the system to actually make cardiac examinations. So an option key is something that is basically used to unlock that particular thing. It's very, very common in ultrasound systems and in CT systems that you must purchase options for you to be able to use particular aspects of the system. Okay. And now to the other modality, which is CT scan. Um, a CT scan is basically a rotating X-ray. So you have, as you said, a tube and a detector that are opposite to each other, and the body is between. This thing is rotating and making different images every many times per second, okay, many times per revolution. So it images the body from different directions. All that data is sent into the host computer, which then reconstructs this to create a 3D image of the body, and can actually create a 3D illustration of the body and of the vessels and of the bones and all of these other things, if you need to do something like that, right? um, and I know that everybody, you're always listening and you're hearing, 2 slice machine, 16 slice, 32 slice, 64 slice, 128 slice, and generally sometimes you might wonder what exactly does that mean. So the detector, which is responsible for translating the x-rays into an actual image for CT scan machines, um, if you look towards what he calls the Z direction as the patient is going into the CT scan machine, okay, the detector across on the length of the patient can have many different image acquiring sections, okay. So when we talk about slice, what basically we mean are the number of individual acquiring detectors on the main detector. Okay, so if you talk about like a 2 slice system, it means that um, across the length of the patient, so let's assume this is the hand, across the length it takes maybe it's just half, right? So one image here, one image here. If you talk about 16 slice system, now if this is the length of the detector, it's divided into 16 different parts, or rather independent acquiring modules of x-rays, right? So across the 16 of them, each of them gives a signal. In essence, what it means is that you're able to image this hand, maybe all of it, by just one revolution in maybe like a 64 slice system, because the detector is this thick. So just by it rotating once, you already have taken an image of this part, this part, this part, this part, this part, this part, all the different parts, and you're able to create an image. So that is the main differentiator between CT scan systems. And it's one of the things that are very common in the specifications for CT scan systems. How many slices does this machine have? Its importance is that you're able to image faster, and um, especially when it comes to angiography, which is basically CT scan of the heart. You are able to maybe image the heart, the whole of the heart at once. Okay, so you can see whether the heart is actually working the way it's supposed to work, if you have a larger slice system, because you can see it all at once. So you can exactly tell that this particular vessel is blocked, something is happening here, this thing is working this particular way for our larger slice systems. And now we are having systems that are, I think, the the most advanced one was I think 640 slice system that was from Toshiba, now Canon. I don't know whether there are newer ones that are more advanced than that, but that used to be the most advanced CT scan that I used to know of, maybe. Yeah, and then uh, one other thing important in majority of CT scan rooms is you'll have contrast injector pump. Um, the injector pump is basically a syringe that is used to inject um, an, a radiation opaque material into the vessels of the patient for imaging of blood vessels. What I'm saying is, you inject something that a liquid that prevents X-rays from passing into the blood vessels of somebody, and then you make a CT scan of that person or an X-ray, and then you are able to tell if the vessels are actually maybe constricted or blocked for that particular patient. So it's a common thing that you will find in CT scan rooms, the injector pump, and it allows for imaging of blood vessels mainly. That's what it's used for. Okay, so I think that's it about the modalities. Um, so um, I will go into, as engineers, our job is generally to maintain the life cycle of the system. So in essence, what that means is you need to install the system, you need to maintain the system, you need to service the system. If it breaks down, you need to repair it. If it requires an upgrade, you need to do that, and eventually, retiring even systems. Okay, and to be able to do that, um, um, you need to have one major thing. Of course, you need to have some tools and some knowledge, but one major thing that you need to have is the service manual. Every system that exists in the world, every medical system has a service manual. It is not possible for any single person to know a system in depth from a service engineer's perspective. It's not. It's literally not possible. So you have to keep on referring back to the manuals. Every system has a manual, and I would say that um, the number one rule of engineering is please read the manual. Okay, and in the manual there are four different um, important parts that will be in every single manual. Doesn't really matter whether it's a mind ray system, doesn't matter. Four parts will always be in the manual. We have what we call the theory of the operation. In Siemens system, they call it the functional description. Um, in G, they call it theory of operation. Also, Philips, they call it the same thing. Okay, the functional description, rather the theory of operation, generally tells you how the system is made from a bird's eye perspective. It tells you the different components that exist in the system, how they are connected, what connects them together, and how generally they are working. The second part that you'll have in every manual is a troubleshooting guide. Troubleshooting guide generally tells you you have a particular problem in a particular place, check on this, check on that, check on this other thing. Okay, it's gonna be there in every single manual. The number three thing is what we call the replacement procedures. So you're having something like a CT scan machine, very many parts inside, or an ultrasound machine, very many parts inside. How do you know how to remove a particular part? Because you remove it wrongly, it gets damaged, then generally you have lost the system, right? So replacement procedures generally tell you how to remove any single part, how to reassemble it. After changing of a particular spare part, it tells you what are the actual um, important things to do once you have changed the part. It might need you to reprogram the part. It might need you to do something kind of a change. Okay, so in every single manual, you'll have the replacement procedures that generally guide you on how to do spare part changes. And then the fourth most important part is the replacement parts. Um, all systems have in the manual a replacement procedure and spare parts. The spare parts, in majority of the manuals, they are called FRU. Okay, so FRU stands for field replaceable unit. What that means is that in the manual, they will give you a particular model number or other part number and indicate whether this is something that can be replaced in the field. Okay, while the machine is working in a particular facility or something of the sort, and it'll give you the part number that then you can use to order for the particular part. um, it will give you what parts are compatible with what parts, because sometimes they make a differences and they change the part number. They generally tell you if this part is compatible with that particular system. Okay, so that when you're purchasing it for a spare part or you're trying to change a spare part for the system, you actually know whether this thing is going to work. Okay, those are the four things. In physical system boards, you will have a sticker that generally will have the part number of the board. So that's another way to actually know what parts that you're looking for or they're trying to find. Okay. Uh, one uh, mm, for the parts and for the service industry for biomedical engineering, we have what we call OEMs, which are original equipment manufacturers. So these are the actual companies that have manufactured the system, maybe Philips, Siemens, GE, Toshiba, Canon, Hitachi, whichever this company is, who has actually manufactured the system. So those are called OEMs. And then you have distributors, which are companies that have been given the job of selling and maintaining systems on behalf of the OEM in terms of a contract. And the other guys that exist in that landscape are what we call independent service organizations, which is what MEMS imaging is. We are not affiliated to a particular company, but we possess the knowledge and the skills to repair these systems from these particular companies. So in a similar way, for parts, there are two options. You can get parts directly from the manufacturer, which are new parts, never been used, probably tested, da, da, da. Or you can get third-party parts, which are parts that are supplied by companies such as ours and some other companies from the US. Even India, they have a lot of companies that do this. You actually buy quite a lot of spare parts from India. And these are used spare parts. Generally, what it means is that somebody somewhere bought a CT scan machine that was probably not working. They discovered, okay, maybe the tube is damaged in the CT scan. All right, let us sell all the other different parts, what are called the third party parts. And it is actually a much more affordable option for systems management, third party parts, rather than original equipment manufacturer parts, rather new parts. So those are the two types of places that you can actually find these things. In maintenance of all these modalities, we have two different kinds of maintenance. One we call corrective maintenance and one we call preventive maintenance. Corrective maintenance is basically the machine has broken down, you're gone there to repair it. Okay. Preventive maintenance, or what you rather hear more often, is PM. PM is the system is working well. You just need to maintain it to ensure that it keeps on running. Similar to your car, you need to go and change oil to ensure that the system continues on running. So the PM is what we call servicing of the system, and it exists across all of them. Majority of PM schedules are 6 months. Some systems, such as CT scan, they say you need to do it quarterly. So every sorry, my video is terrible. I don't know why. Okay. Yeah. So PM schedule, where CT scan systems, they talk about needs to be done quarterly, so 3 times per year. Ultrasound systems talk about maybe 6 months. X-ray systems are also around 6 months, and all the different PM schedules have something differently that they work with. Okay. Yeah, have something different that they work with. Let me just move to a different side. Okay, I think that's better. Yeah. So yeah. So for PMs, PM for systems, in something like ultrasound systems, majority of the time, what you really need to check out for is dust in the system. Yeah, basically mainly dust and dry joints. Ultrasound systems. For X-ray systems, what you need to check is that the technique has not actually shifted. If you want to do 40 kV, you need to be able to actually get 40 kV and nothing more than that. There are actually small machines that are used to actually measure the amount of kV, and then you are able now to do calibration for the system. to make sure that it actually delivers what you have asked for it from it. Um, in And also for X-ray systems, you need to check for the table. If it's a floating table, you need to grease the table, the chest stand, and of course dust. For CT scan machines, a major part of the PM is what we call the slip ring. So you have this thing that is rotating. The connection between the rotating part and the stationary part is mainly done through what we call a slip ring, which is a copper ring and some graphite contacts around the copper ring. So one major part for it is to clean the copper rings. For service on the CT scan is to actually clean the copper rings. Of course, again, dust, and because this thing is rotating, there is greasing, and also for the table going up and down, in and out, there's also greasing for that. And software change, or rather software updating or installing software afresh for the system. Okay, remember I told you that all of these systems, how they are made is that you have general purpose operating system, either Windows or Linux, and then you have an application on top of it. By design, from my experience, they are not very stable. So you're always having small software issues with these systems, almost always. That requires you to do software reload on the system. For GE systems, they call it load from cold, which means a fresh install of the system. Other things, they call it different things, but all the same thing. It's basically a refresh of the software of the system. Okay. Of course, as engineers, the number one thing you need to understand is you need to document your work, and how you document your work for repair work that is done in the system or service work that is done in the system is they're called service reports. So job card, service report, same thing, yeah. Where generally a service report will include number one, the date of actually doing the work. Number two will be what system it is. That thing will be what was the problem that you encountered, what was the diagnosis, or where the problem is coming from, what was the correction for that particular problem. The other thing that always is there is that what kind of a part was used to repair that particular system, if at all a part was used. And then the other thing is the amount of time that was spent working on that particular system. In all working, there are two different times. There's time to travel and there's time to fix. All of this is normally accounted for in terms of service engineers who actually repair that system. Okay, so I want to speak a little bit about the career pathways that exist in biomedical engineering from as we're starting out. So, um, in essence, we have around 3 different places where an engineer gets some work to do. So, number one is as a biomedical engineer that is domiciled in the hospital, whose major job is to manage the X-rays, the systems, general, the all the imaging systems that are existing in the hospital. The biomedical engineer at this hospital base mainly develops into a manager for the systems that exist there. By design, because you're working with so many different systems, many of the times you will not end up as an expert for particular modalities. You're dealing with theater systems, you're dealing with point of care systems, you're dealing with the x-rays, the ultrasounds, the furniture for the hospital. Is very difficult to become an expert at a particular modality, but then you're able to have a much bigger world view of these systems. The second place that goes into is as service engineers. So service engineers, which generally is what we do, are people that are specialized towards particular systems. Okay, so you have service engineers that are geared toward laboratory equipment. Some of them are towards theater systems, which are called life care systems, LCS. Uh, yeah, LCS. Some engineers are, focused on imaging systems such as ourselves. Others are focused on oxygen, oxygen plants, all these different things. Uh, because of the range of all of these systems, majority of the time you focus on a particular thing. If you are doing laboratory equipment, you do laboratory equipment. For us, we do imaging equipment, and it allows us to become experts at these particular systems. And many engineers, work with a particular company. So, there's an engineer who only does GE systems, maybe GE X-ray, GE ultrasound, GE CT, GE MRI, whatever. Uh, and that's okay. There are more than enough systems for you to learn, even if you're just in one particular company. For our company, we are multi vendor, so we are working with different manufacturers because you have the knowledge and you are able to do that. We work with different manufacturers, and that's one other way that somebody else can actually do this. The other place for biomedical engineers is in obviously research and manufacture, where engineers are working as design engineers for companies that manufacture these systems or create these systems. So in countries that have a strong manufacturing sector, of course, like India, there are engineers that actually go into design rather than life cycle management, going to design of these systems. Yeah, and they're able to determine where we go forward. For like our for like my field, generally you start out as a trainee. You know, you learn a little bit about this, then you work under somebody as a junior engineer. Over time you gain experience, then you become you can call a senior engineer. You're able to actually produce a project, and from there is to become a support engineer, where generally you're able to support other engineers that are working in the field and direct them on how to go about repair of some of these systems. In all the manufacturers, that is similar. There's a similar kind